What if I told you that right beneath your feet, there's a ball of molten metal spinning at temperatures hotter than the surface of the sun? And what if I told you that this scorching furnace is the only reason you're alive right now? Because in the next few minutes, we're going to explore one of the most terrifying scenarios imaginable. What happens if Earth's core suddenly, instantly goes cold? Now, before you click away thinking this is just another doomsday fantasy, let me paint you a picture. The coffee you're drinking, the chair you're sitting on, the very ground beneath your building, all of it exists in a delicate balance that depends on something most people never think about. A 2,400 kilometre wide sphere of liquid iron and nickel, churning away 6,400 kilometres below the surface, generating forces so powerful they literally hold our world together. But here's what's going to blow your mind. This isn't just some random rock floating in space. Earth is essentially a giant machine, and like any machine, it has moving parts. The core is the engine, the mantle is the transmission, and the crust is just the thin shell we happen to live on. And just like any engine, if it suddenly stops working, everything else falls apart in ways you can't imagine. I'm going to walk you through exactly what would happen, step by step, minute by minute, as our planet dies from the inside out. We'll explore why the magnetic field would vanish first, how the very ground would start sinking, and why the oceans would begin to boil while simultaneously freezing. Sounds impossible? Stick around, because the science behind this catastrophe is more fascinating and more terrifying than any science fiction movie ever made. And here's the thing that really gets me about this scenario. Most people think about asteroid impacts or supervolcanic eruptions when they imagine the end of the world, but those are quick, dramatic events. What we're talking about today is something far more insidious, a slow-motion apocalypse that would unfold over days, weeks and months, giving humanity just enough time to watch everything they've ever known crumble away. But first, let me give you some context about what we're actually dealing with here. The Earth's core isn't just hot, it's approximately 5,000 to 6,000 degrees Celsius. To put that in perspective, that's hotter than the surface of the sun, which sits at around 5,500 degrees. This isn't some distant theoretical knowledge either. We know this because of how seismic waves travel through the planet, how heat flows to the surface, and dozens of other measurements that paint a picture of our planet's interior. Now, the core is actually made up of two parts. There's the inner core, which is solid iron and nickel under incredible pressure, and the outer core, which is liquid. This liquid outer core is constantly churning, spinning, convecting, driven by the heat from radioactive decay and leftover energy from when Earth first formed 4.6 billion years ago. And this motion, this constant swirling of molten metal, is what generates Earth's magnetic field. Think of it like a massive dynamo, a generator the size of Mars spinning inside our planet. The magnetic field it creates extends far out into space, forming what scientists call the magnetosphere. This invisible shield deflects most of the solar wind, those charged particles constantly streaming out from the sun that would otherwise strip away our atmosphere and fry everything on the surface. But in our scenario, all of that stops, instantly. The temperature drops from 6,000 degrees to, let's say, room temperature, 20 degrees Celsius. The liquid outer core solidifies in seconds, the convection stops, the dynamo shuts down, and the first thing that happens, the very first consequence of this impossible event, is that Earth's magnetic field begins to collapse. Now, magnetic fields don't just disappear instantaneously. They fade, and the speed at which they fade depends on the size of the system. For a planet-sized magnetic field, we're talking about a collapse that happens over several hours to maybe a few days. But from a geological perspective, from the perspective of a planet that's been magnetically active for billions of years, this is essentially instantaneous. Within 24 hours, maybe 48 at the most, the magnetosphere is gone. Earth becomes magnetically naked, exposed to the full fury of space weather, and the first thing you'd notice, if you were paying attention, is the auroras. Those beautiful dancing lights that normally only appear near the poles would suddenly be visible everywhere. London, Tokyo, Mexico City, all of them would be treated to incredible light shows as charged particles from the sun slam directly into our upper atmosphere. But this isn't a good thing. Those particles carry energy, and when they hit our atmosphere, they start heating it up and stripping it away. The same process that turned Mars from a potentially habitable world into the cold, thin-air desert it is today begins happening to Earth. Not quickly, not in days or weeks, but the process starts, and once it starts, it doesn't stop. Meanwhile, something even more dramatic is happening deep underground. Remember, we've just instantly cooled a ball of molten metal that's been at 6,000 degrees for billions of years. The physics of what happens next is absolutely mind-bending. When materials cool down, they contract. This is basic thermal expansion and contraction, something you can observe with any piece of metal, but we're talking about cooling down a sphere that's 2,400 kilometers across. The amount of contraction we're dealing with is enormous. The inner core, which was already solid but extremely hot, suddenly shrinks. The outer core, which was liquid, not only solidifies but contracts dramatically as it does so. This creates what geophysicists call a volume deficit. Suddenly there's less material taking up space at the center of the planet. The result? Everything above it starts to collapse inward. The mantle, that thick layer of hot rock that sits between the core and the crust, begins to sink toward the center of the planet. Now the mantle isn't empty space. It's made of rock, incredibly hot rock, that's been kept in a semi-liquid state by the heat from the core. This rock moves, but it moves slowly, flowing like an incredibly thick fluid over geological timescales. Convection currents in the mantle are what drive plate tectonics, what cause earthquakes and volcanic eruptions, what shape the surface of our planet. But with the core suddenly cold, two things happen to the mantle simultaneously. First, it starts cooling from below for the first time in Earth's history. Second, it starts collapsing inward to fill the space left by the contracting core. The combination of these two effects creates a geological nightmare. The cooling happens relatively quickly. Rock is a decent conductor of heat, and when you suddenly place cold material next to hot material, heat flows from hot to cold until they equalize. The mantle closest to the core starts cooling and solidifying, becoming more rigid. But at the same time, it's under incredible gravitational stress as everything above it presses down, trying to fill the void left by the shrinking core. The result is that the mantle begins to crack. Not surface cracks, but deep, fundamental fractures that extend hundreds of kilometers into the planet. These aren't like the fault lines we're familiar with on the surface. These are structural failures on a planetary scale, cracks that would make the San Andreas Fault look like a hairline fracture in a piece of pottery. And when the mantle cracks, when these deep structures fail, the energy released is unimaginable. We're talking about earthquakes that don't register on any scale we've ever devised. Magnitude 15, magnitude 20 earthquakes that would be felt on the opposite side of the planet. The ground wouldn't just shake, it would ripple like water, with waves of solid rock rolling across continents. But here's where it gets really interesting and really terrifying. The surface of the Earth, the crust we live on, is floating on top of the mantle. It's like a thin shell, averaging only about 30 kilometers thick on continents and even thinner under the oceans. When the mantle starts collapsing and cracking, the crust has nowhere to go but down. Imagine you're standing on a frozen pond and someone suddenly drains all the water from underneath the ice. The ice doesn't just crack, it collapses entirely. That's what would happen to Earth's crust, except instead of falling a few meters into a pond, it would be falling hundreds of kilometers into a fractured cooling mantle. Mountain ranges would simply disappear, not from erosion or weathering, but from the ground beneath them literally giving way. The Himalayas, the Rockies, the Andes, all of them would sink into the planet like stones dropped into water. Ocean basins would tilt and fold as the seafloor collapsed unevenly. Entire continents would crack apart and slide into the growing void. And all of this would happen relatively quickly, not instantly, but over days to weeks rather than the millions of years geological processes usually take. The cooling of the core would trigger a cascade of structural failures that would essentially cause the solid surface of the planet to cave in on itself. But wait, because we're not done yet. While all of this geological chaos is unfolding, something equally dramatic is happening to our oceans and atmosphere. The heat from Earth's core doesn't just drive geological processes, it also plays a crucial role in regulating our planet's temperature and weather patterns. Deep ocean currents, the massive conveyor belts of water that circulate heat around the globe, are partially driven by geothermal heat from the seafloor. This heat comes from volcanic vents, underwater volcanoes, and the general warmth that radiates up from the mantle. When the core cools, this heat source disappears almost immediately. The first thing you'd notice is that the deep ocean starts getting cold. Not surface cold, but deep, bone-chilling cold that starts at the bottom and works its way up. The thermohaline circulation, the global system of ocean currents that helps regulate Earth's climate, begins to shut down as the temperature gradients that drive it disappear. This has immediate consequences for weather patterns around the world. The Gulf Stream, which keeps Western Europe warm despite its northern latitude, weakens and eventually stops. The Antarctic circumpolar current, which isolates Antarctica and helps maintain its ice sheets, changes direction and intensity. Weather systems that have been stable for thousands of years suddenly become chaotic and unpredictable. But the really strange part, the part that would confuse anyone trying to understand what was happening, is that while the deep ocean is getting colder, the surface might actually start getting warmer in some places. This is because all that heat that was previously flowing steadily from the core to the surface is now being released all at once as the mantle cracks and shifts. Massive amounts of stored thermal energy, heat that's been building up over geological time, suddenly have new pathways to reach the surface. Volcanic activity would initially increase dramatically as the fractured mantle allows magma to reach the surface more easily. Geysers and hot springs would appear in places that have never had them before. The ground itself would start radiating heat as deep, hot rock is exposed by the collapsing crust. So you'd have this bizarre situation where the planet is cooling from the inside out, but the surface is experiencing a massive heat wave from all the thermal energy being suddenly released. It would be like watching a building collapse while simultaneously catching fire. And this is where things get truly surreal, because while the surface is experiencing this chaotic release of thermal energy, the lack of internal heat generation means that Earth's overall energy budget is collapsing. Think about it this way. The core has been acting like a massive furnace for 4.6 billion years, constantly pumping heat outward through convection, conduction, and radiation. That steady flow of energy has been keeping the mantle hot and pliable, maintaining the delicate balance that allows plate tectonics to function. But now that furnace is off, permanently, and the effects ripple outward through every system on the planet, the first major atmospheric consequence would be the collapse of the jet streams. These high-altitude rivers of air that circle the globe are powered by temperature differences between the equator and the poles, but they're also influenced by heat rising from the surface. With geothermal heat patterns changing dramatically as the crust collapses and hot mantle rock gets exposed in random locations, the jet streams would become completely unstable. Weather systems that normally move in predictable patterns would stall out or reverse direction entirely. Hurricanes might form in the middle of continents as hot spots in the fractured crust create massive thermal updrafts. Arctic air masses could suddenly plunge toward the equator as the normal circulation patterns break down. The result would be weather chaos unlike anything in recorded history. But here's what really keeps me awake at night thinking about this scenario: the feedback loops. In Earth science, we talk a lot about feedback loops, systems where the output of a process affects its own input. Usually these help maintain stability, but when they break down, they can accelerate catastrophic changes. Consider what happens to Earth's albedo, its ability to reflect sunlight back into space. Normally, ice and snow at the poles reflect a significant amount of solar radiation, helping keep the planet cool. But as the deep ocean currents shut down and weather patterns become chaotic, the distribution of ice and snow changes dramatically. Some areas might see unprecedented ice formation as cold, deep ocean water reaches the surface, while others might experience rapid melting as hot spots in the crust heat the ground. The changing ice coverage affects how much solar energy Earth absorbs, which affects atmospheric circulation, which affects weather patterns, which affects ice formation, and on and on. These feedback loops, which normally help stabilize Earth's climate, would become amplifying cycles driving the system further and further from equilibrium. And then there's the volcanic situation, which deserves its own terrifying chapter in this story. Volcanic activity on Earth is normally controlled by the steady, predictable movement of tectonic plates and the gradual rise of magma through established channels. But when the mantle starts collapsing and cracking, all bets are off. Imagine the world's most dangerous volcanoes, the supervolcanoes like Yellowstone Toba and the Campi Flegrei, suddenly losing the structural integrity that's been containing their massive magma chambers. The collapsing crust doesn't just create new pathways for magma to reach the surface, it also changes the pressure dynamics that have been keeping these sleeping giants dormant. Yellowstone alone contains enough magma to bury the entire United States under several feet of volcanic ash. Under normal circumstances, this magma is held in check by the weight and structure of the overlying rock. But if that rock starts collapsing into a fractured, cooling mantle, the pressure containment fails catastrophically. We wouldn't just be looking at one supervolcanic eruption, we'd potentially be looking at multiple simultaneous eruptions as volcanic systems around the world lose containment at the same time. The amount of ash, gas, and debris thrown into the atmosphere would be enough to block out the sun for months, maybe years. This is where the scenario becomes almost paradoxically complex. You'd have a planet that's cooling from the inside out, releasing massive amounts of stored heat through volcanic activity and crustal collapse, while simultaneously being plunged into a volcanic winter that blocks solar radiation and drives surface temperatures down dramatically. The atmospheric chemistry would become completely unstable. Volcanic eruptions would pump enormous quantities of sulfur dioxide, carbon dioxide, and other gases into the atmosphere. The sulfur dioxide would form aerosols that reflect sunlight, contributing to the cooling effect, while the carbon dioxide would create a greenhouse effect, trapping what little heat remained. But here's the kicker. With the magnetic field gone, these atmospheric gases would be vulnerable to being stripped away by solar wind. So while volcanic activity is pumping gases into the atmosphere, space weather is simultaneously blowing them away into space. The atmosphere itself would become a battleground between volcanic input and solar stripping. Ocean chemistry would face similar chaos. The collapse of deep ocean circulation would cause massive dead zones, as oxygen-rich surface water stops mixing with deeper layers. At the same time, volcanic activity would be pumping acidic compounds into seawater, dropping the pH and making the oceans increasingly hostile to life. Marine ecosystems would face a triple threat: temperature chaos from the disrupted circulation, chemical changes from volcanic emissions, and potential loss of atmospheric protection from the collapsed magnetic field. Fish kills would be measured not in thousands or millions, but in entire species disappearing within weeks. And yet, in some bizarre way, life might initially flourish in certain areas. The hotspots created by exposed mantle rock could become oases of warmth in an increasingly cold world. Bacterial communities that thrive in extreme heat, the kind found around deep-sea volcanic vents, might suddenly find new habitats as the planetary surface becomes pockmarked with geothermal features. But this would be a temporary reprieve at best. The fundamental energy source that has powered Earth's biosphere for billions of years would be gone. Plants depend on stable weather patterns and predictable seasonal cycles. Animals depend on stable food webs and habitable temperature ranges. The collapse of Earth's internal heat engine would unravel these systems faster than evolution could adapt. Agricultural collapse would be inevitable and swift. Even if some regions initially became warmer due to exposed hot rock, the soil itself would become unstable as the crust fractured and shifted. Farmland that had been productive for thousands of years would literally fall into cracks in the earth or be buried under debris from collapsing mountains. The timing of this agricultural collapse would be crucial for human survival. If it happened during growing season in major agricultural regions, food reserves would be inadequate to sustain populations through the chaos. If it happened during winter, there might be slightly more time to organize a response, but the window would still be measured in months at most. Urban infrastructure would face catastrophic failure on multiple fronts. The massive earthquakes from mantle collapse would exceed the design limits of every building, bridge and tunnel ever constructed. Power grids would fail not just from structural damage, but also from the electromagnetic effects of the collapsing magnetic field. Communication satellites would be fried by solar radiation, cutting off global communications just when coordination would be most critical. Water systems would be particularly vulnerable. Most major cities depend on complex networks of pipes, pumps, and treatment facilities that require stable ground and reliable power. When the ground starts shifting hundreds of meters vertically and power systems fail simultaneously, clean water becomes unavailable almost immediately. But perhaps the most psychologically devastating aspect of this scenario would be the timescale. Unlike a nuclear war or asteroid impact, which would be over in hours or days, the collapse triggered by a cooling core would unfold over weeks and months. Long enough for people to understand what was happening, long enough to watch the systematic failure of every system that supports modern civilization, but not long enough to do anything meaningful to stop it. The human response would likely follow predictable patterns: initial disbelief, then panic, then desperate attempts at survival and adaptation. Governments would declare martial law and attempt to maintain order, but how do you maintain order when the ground itself is collapsing? How do you evacuate populations when there's nowhere safe to evacuate to? Some groups might attempt to build underground shelters, trying to ride out the surface chaos in deep bunkers. But even the deepest human-made structures would be vulnerable to the planetary-scale geological failures we're describing. A bunker that's safe from nuclear war becomes a death trap when the bedrock it's built in starts fracturing and shifting. The irony is that the very thing that makes Earth habitable, that molten core spinning beneath our feet, is so fundamental to every system on the planet that its loss would trigger a cascade of failures touching every aspect of existence. From the largest geological processes down to the smallest biological systems, everything depends on that deep, invisible heat source that most people never even think about. And this brings us to perhaps the most unsettling realization of all: how utterly dependent we are on forces completely beyond our control or even our direct observation. We like to think we're masters of our environment, that technology and human ingenuity can overcome any challenge. But this scenario reveals the uncomfortable truth that we're passengers on a planetary machine we barely understand, let alone control. Every breath you take, every step you make, every thought you think exists because of a ball of molten metal spinning in perfect darkness, thousands of kilometers below your feet. And here's what makes this even more mind-bending. The cooling wouldn't just affect Earth's geology and climate, it would fundamentally alter the planet's relationship with space itself. You see, Earth's magnetic field doesn't just protect us from solar radiation, it also affects how our planet interacts with cosmic rays, interplanetary dust, and even the fabric of space-time in our local region. Without that magnetic shield, Earth would become a sitting duck for every piece of high-energy debris floating through the solar system. Cosmic rays that normally get deflected away would slam directly into our atmosphere, creating cascades of secondary particles that would irradiate everything on the surface. The Van Allen radiation belts, those protective zones of trapped particles that surround our planet, would dissipate within days. But here's where the physics gets truly bizarre. The loss of Earth's magnetic field wouldn't just expose us to more radiation, it would actually change how particles and energy flow through the space around our planet. Think of Earth's magnetosphere as a rock in a stream, diverting the flow of charged particles from the Sun. Remove that rock and the stream patterns change completely. This creates what scientists call a magnetospheric cavity, a region where the normal structure of space weather breaks down entirely. Solar wind particles that used to be deflected hundreds of thousands of kilometers away would now penetrate directly to Earth's upper atmosphere, dumping their energy into our air and heating it to temperatures we've never experienced. The thermosphere, that layer of atmosphere about 100 kilometers above the surface, would start expanding dramatically as it absorbs this incoming energy. Normally, this layer is kept in check by Earth's magnetic field and the steady heat output from below. But with magnetic protection gone and internal heat failing, it would become wildly unstable. Satellites in low Earth orbit would find themselves flying through increasingly dense atmosphere as the thermosphere expands upward. The drag would cause them to spiral downward and burn up in spectacular meteor showers that would light up the sky for weeks. The International Space Station, GPS satellites, communication networks, all of it would come crashing down in a rain of burning metal and debris. And this is just the beginning of the space-related chaos. You know how I mentioned that volcanic activity would initially spike as the mantle cracked and shifted? Well, some of those volcanic eruptions would be powerful enough to literally blast material into space. We're talking about volcanic plumes reaching heights that would make Mount Vesuvius look like a backyard campfire. The combination of expanding atmosphere and volcanic debris would create a cloud of particles around Earth unlike anything in the planet's history. This debris field would interfere with the radio communications, create false meteor showers as particles burned up in the atmosphere, and potentially even affect the orbit of the Moon by creating drag on its gravitational interaction with Earth. Speaking of the Moon, here's something that'll keep you up at night. Earth's cooling core would affect our relationship with our closest celestial neighbour in ways that seem almost impossible to believe. The Moon's orbit is gradually expanding due to tidal forces, but this process depends on energy transfer from Earth's rotation. With the core no longer generating the convection currents that help drive plate tectonics and maintain rotational stability, Earth's spin would begin to change. It's not that the planet would suddenly stop spinning, but the distribution of mass inside Earth would shift as the core contracted and the mantle collapsed. This would affect the moment of inertia, changing how fast the planet rotates. It's like a figure skater pulling their arms in during a spin, except in reverse. As mass moves inward toward the collapsed core, Earth's rotation would actually slow down. Days would start getting longer, not by seconds or minutes, but potentially by hours over the course of weeks. The tidal relationship with the moon would become unstable, possibly causing our satellite to either spiral inward or drift away more rapidly than normal. The tides themselves, which billions of years of life have adapted to, would become chaotic and unpredictable. Coastal regions that have never experienced extreme tides would suddenly be flooded by walls of water, while traditional tidal zones might find themselves high and dry. Marine life that depends on tidal rhythms for feeding, breeding, and migration would face immediate extinction as these ancient patterns collapse overnight. But let's zoom back down to the human scale for a moment, because while all this planetary chaos is unfolding, individual people would be experiencing something that no human in history has ever faced: the complete breakdown of every system that makes modern life possible, happening simultaneously across the entire globe. Imagine you're in New York City when this begins. The first sign might be unusual aurora activity, visible even through the city's light pollution. Then the earthquakes start, not the rolling motion you might expect, but sharp, violent jolts as the bedrock itself begins to fracture. Buildings that have stood for decades suddenly develop cracks that spread like spiderwebs across their facades. The subway system, built on the assumption that Manhattan's bedrock is essentially permanent, would become a death trap as tunnels collapse and flood with groundwater, displaced by the shifting geology. Central Park, that carefully maintained oasis of green in the urban jungle, would develop sinkholes and fissures as the ground beneath it literally falls away. Power would fail not just from earthquake damage, but from electromagnetic interference as Earth's magnetic field collapses. The electrical grid, designed to handle normal variations in magnetic activity, would be overwhelmed by the chaotic electromagnetic environment. Transformers would explode, power lines would arc and fail, and backup generators would be useless without fuel deliveries that can no longer get through. Water pressure would drop to zero as pumping stations fail and underground pipes crack and shift. The Hudson River, which has carved its path over thousands of years based on stable geological conditions, would change course as the landscape literally reshapes itself. What was once a navigable waterway could become a series of rapids, waterfalls, or dry channels as the riverbed tilts and fractures. And this isn't just happening in New York. This same scenario is playing out simultaneously in London, Tokyo, Sao Paulo, Mumbai, every major city on Earth. The global nature of the catastrophe means there's no safe place to evacuate to, no unaffected region that could provide aid or shelter. Air travel becomes impossible not just because airports are damaged, but because the atmosphere itself becomes too chaotic and debris-filled to navigate safely. The jet streams that commercial aviation depends on for efficient flight paths would become violent, unpredictable torrents of air moving in directions that change by the hour. Commercial shipping faces similar challenges as ocean currents become unstable, and coastal ports are either destroyed by earthquakes or made inaccessible by changing sea levels. The global supply chain that keeps supermarket shelves stocked and hospitals supplied with medicine would collapse within days. Food production would face a triple catastrophe: farmland rendered unusable by geological instability, transportation networks destroyed, and climate chaos that makes it impossible to predict growing conditions. Even in regions that initially avoid the worst geological damage, crops would fail as temperature swings, altered precipitation patterns, and atmospheric chemistry changes create conditions unlike anything in agricultural history. The psychological impact on survivors would be almost as devastating as the physical destruction. Humans are remarkably adaptable, but we depend on certain constants: the ground being solid, the sun rising and setting predictably, the basic laws of physics working the way they always have. When those constants disappear, when the very foundation of reality becomes unstable, the mental health consequences would be unprecedented. People would be forced to watch their entire world, not just their personal lives but the physical world itself, disintegrate in real time. The helplessness would be absolute. There would be no enemy to fight, no disaster to clean up from, no way to rebuild because the destruction would be ongoing and accelerating. Religious and philosophical systems would struggle to provide meaning in the face of such complete systemic failure. How do you maintain faith when the planet itself seems to be dying? How do you find purpose when every human achievement, every work of art, every relationship faces imminent destruction through forces beyond any possible human response? Yet even in this scenario, human nature suggests that some people would try to maintain normalcy, to preserve what they could of civilization and culture. Libraries would attempt to protect books, museums would try to safeguard artifacts, teachers would continue educating children even as the world crumbled around them. These acts wouldn't change the outcome, but they would represent something essentially human: the refusal to surrender meaning even in the face of meaningless destruction. Small communities might fare better than large cities, at least initially. Rural areas with less infrastructure to fail, and populations more experienced with self-sufficiency, could potentially ride out the first waves of chaos. But even they would face challenges that no amount of preparation could overcome. Farming communities would find their fields literally falling into cracks in the earth. Water wells would either run dry as aquifers shifted, or become contaminated as geological layers that have been stable for millions of years suddenly mixed together. Livestock would panic and scatter as their instincts, evolved over millions of years to respond to natural disasters, encounter something completely unprecedented. The seeds that farmers save for next year's planting would become useless, as growing conditions changed so rapidly that no crop could adapt. Wild animals would face similar challenges as their habitats disappear, not gradually through human development, but suddenly through geological collapse. Forests would be particularly vulnerable. Trees depend on stable soil conditions and consistent weather patterns. As the ground shifts and climate becomes chaotic, entire ecosystems would collapse within weeks. The Amazon rainforest, the boreal forests of Canada and Siberia, the ancient redwood groves of California, all of them would face destruction not from human activities, but from the failure of the geological systems that have supported them for millennia. The loss of these forests would accelerate atmospheric changes, removing crucial carbon sinks just when the atmosphere is already being destabilized by volcanic emissions and the loss of magnetic field protection. Oxygen levels would begin to fluctuate as plant life dies off, and the normal cycles of photosynthesis and respiration break down. Ocean ecosystems would face similar cascading failures. Marine food webs depend on predictable patterns of temperature, salinity, and current flow. As these patterns collapse, entire species would find themselves in water that's too hot, too cold, too acidic, or simply moving in the wrong direction for their life cycles to complete. Coral reefs, already under stress from human activities, would face complete bleaching as water temperatures fluctuate wildly. The Great Barrier Reef, the Caribbean reefs, the coral atolls of the Pacific, all would become underwater graveyards within months. Fish populations would crash not just from habitat loss, but from the disruption of migration patterns that have been stable for millions of years. Salmon wouldn't be able to find their spawning grounds as rivers change course. Whales would become disoriented as the magnetic cues they use for navigation disappear. Seabirds would starve as the fish they depend on vanish from traditional feeding areas. But here's what really haunts me about this scenario. The timescale gives people just enough time to understand what's happening, but not enough time to adapt. If the core cooling happened over millions of years, life might evolve new strategies to cope. If it happened in seconds, it would be over too quickly for conscious suffering. But happening over weeks and months means watching everything die slowly, understanding the inevitability, and being powerless to change it. The human response would likely fracture along predictable lines. Some groups would turn to denial, insisting that the disasters were temporary, that normal conditions would return. Others would embrace nihilism, concluding that nothing matters if the world is ending. A few might channel their energy into desperate scientific efforts, trying to understand if anything could be done to reverse or mitigate the cooling. But the physics is clear. Once the core cools, there's no mechanism to reheat it. The radioactive elements that have been generating heat for billions of years can't be reactivated. The gravitational energy that heated the core during Earth's formation is already spent. The dynamo that generates the magnetic field can't be restarted without convection in the liquid outer core. This would be a truly irreversible catastrophe, the kind that makes volcanic eruptions and asteroid impacts look like minor setbacks. Those disasters, however devastating, leave behind a planet that's still fundamentally capable of supporting life. The cooling of Earth's core would remove the very foundation that makes a living world possible. And yet, as we contemplate this scenario, it forces us to appreciate something we usually take for granted: the incredible, delicate, beautiful complexity of the system we live within. Every breath you're taking right now exists because of a perfect storm of physics, chemistry, and geology that has been running continuously for 4.5 billion years. The magnetic field protecting you from cosmic radiation, the solid ground supporting your weight, the stable climate allowing plants to grow and produce oxygen, all of it depends on that molten furnace spinning silently in the darkness beneath your feet. We are, all of us, riding on a thin crust above an engine we barely understand, trusting our lives to forces that operate on scales of time and energy that dwarf human comprehension. This thought experiment isn't just about imagining catastrophe. It's about recognizing the extraordinary nature of ordinary existence, the miraculous stability that allows us to build civilizations, create art, fall in love, and contemplate our place in the universe. We live on a planet that is, from any rational perspective, impossible, a ball of rock floating in the vacuum of space, wrapped in a thin layer of gas, warmed by a nuclear reactor 93 million miles away, and kept stable by the churning of molten metal thousands of miles beneath the surface. The cooling of Earth's core would strip away all of these systems one by one, revealing just how dependent we are on forces entirely beyond our control. But it would also reveal something else, the preciousness of what we have right now, in this moment, on this impossible world that somehow manages to support not just life, but consciousness, wonder, and the capacity to imagine our own destruction, and, in doing so, appreciate our survival. The realization of our cosmic fragility brings us to perhaps the most chilling aspect of this entire scenario, the speed at which complex systems unravel when their foundational supports are removed. We've talked about geological collapse, atmospheric chaos, and magnetic field failure, but there's something even more fundamental at stake here. The very concept of equilibrium itself would break down. You see, Earth isn't just a rock with some weather on top. It's what scientists call a complex adaptive system, where countless interconnected processes maintain stability through constant adjustment and feedback. Remove the core's heat, and you don't just lose one component, you lose the organizing principle that keeps everything else in balance. Think about your own body for a moment. Your heart doesn't just pump blood, it maintains the pressure gradients that allow every other organ to function. Stop the heart, and you don't just lose circulation, you lose the coordinated symphony of biological processes that define life itself. Earth's core plays a similar role for our entire planet. The mantle convection that drives plate tectonics doesn't just move continents around randomly. It's part of a planetary thermostat that regulates surface temperature by controlling how much carbon dioxide gets recycled between the atmosphere and the deep Earth. Volcanic eruptions aren't just random explosions, they're pressure release valves that maintain chemical balance in the atmosphere and oceans. When the core cooling disrupts these systems, Earth doesn't just become a different kind of planet. It becomes a planet where the very concept of planetary systems breaks down entirely. The feedback loops that have maintained habitability for billions of years would transform into runaway processes driving the world towards states that have no precedent in Earth's history. Consider the carbon cycle, that elegant dance of chemistry that keeps our atmosphere from becoming either a suffocating greenhouse like Venus or a frozen wasteland like Mars. Plants pull carbon dioxide from the air, animals breathe it back out, ocean chemistry absorbs and releases it, and volcanic activity recycles it from deep storage. The whole system depends on predictable temperature ranges, stable ocean circulation, and regular volcanic activity. But in our cooling core scenario, every part of this cycle breaks simultaneously. Plants die from climate chaos before they can absorb atmospheric carbon. Ocean circulation shuts down, disrupting marine carbon absorption. Volcanic activity becomes either completely absent in some regions or catastrophically intense in others, depending on how the fractured mantle behaves. The result would be atmospheric chemistry unlike anything in Earth's 4.6 billion year history. Not the gradual shifts that allowed life to adapt over geological time, but chaotic swings that would make the atmosphere uninhabitable for any complex life within a single generation. And here's where the scenario becomes almost surreally complex. While the planet is dying from the inside out, the laws of physics would create pockets of temporary habitability that might actually be more extreme than anything we see on Earth today. The hot spots where fractured mantle rock reaches the surface wouldn't just be warm, they'd be superheated zones where the temperature and chemical conditions might actually exceed what we find around deep-sea volcanic vents. These zones would become bizarre oases in an increasingly hostile world, potentially supporting extremophile bacteria and creating localized weather systems that exist nowhere else. Imagine geysers of superheated water shooting hundreds of meters into the air, creating their own microclimates where tropical conditions exist in the middle of what's becoming a global ice age. But these oases would be death traps for complex life. The temperature gradients would be so extreme that moving just a few hundred meters could mean the difference between boiling and freezing. The chemical composition of the air and water would change unpredictably as different parts of the mantle reach the surface, creating an atmosphere that's locally toxic even if it's globally thin. Meanwhile, the regions between these hotspots would experience something unprecedented in Earth's history: true geological death. Areas where the crust has collapsed but no hot mantle has reached the surface would become vast depressions filled with stagnant air and water, cut off from any source of heat or chemical energy. These dead zones would expand outward from the initial collapse points like ripples on a pond, except instead of water, it would be the absence of geological activity spreading across continents. The Rocky Mountains might become a series of cold, empty valleys. The Great Plains could turn into a vast depression where the temperature never rises above freezing and nothing grows. The contrast between the superheated chaos zones and the frozen dead zones would create weather patterns that defy every model we have for atmospheric behavior. Imagine hurricanes powered not by warm ocean water, but by the temperature difference between boiling hotspots and frozen wastelands just a few dozen kilometers apart. These storms wouldn't follow the predictable paths of normal weather systems, because the heating sources would be random and constantly changing as new fractures open and old ones cool. A hurricane might form over a hotspot in what used to be Kansas, then travel east until it hits the frozen dead zone that used to be the Appalachian Mountains, where it would either dissipate instantly or transform into a completely different kind of weather phenomenon. The jet streams, those high-altitude rivers of air that normally flow in predictable patterns around the globe, would become chaotic turbulence as they encounter these random hot and cold zones. Commercial aviation would be impossible not just because of the infrastructure collapse, but because the very concept of predictable air currents would cease to exist. But let's pause for a moment and consider what this would mean for the human experience of time itself. We measure our lives by cycles, days and nights, seasons, years. These rhythms are so fundamental to human psychology that we've built our entire civilization around them. But in our cooling core scenario, these cycles would become meaningless. Days would gradually get longer as Earth's rotation slows, but the length would change unpredictably as the planet's mass distribution shifts. Some days might be 25 hours, others might be 30. The concept of a regular sleep schedule would become impossible, as the most basic rhythm of human existence becomes chaotic. Seasons would disappear entirely, replaced by random climate fluctuations that could swing from Arctic cold to tropical heat within weeks, depending on whether your region was near one of the superheated zones or caught in a frozen dead area. The annual cycles that govern everything from agriculture to animal migration to human holidays would become meaningless concepts from a lost world. Years would still pass, measured by Earth's orbit around the Sun, but they would no longer correspond to any meaningful cycle of renewal or change. Each year would simply bring further decay as the planetary systems continue to break down in unpredictable ways. This temporal chaos would be psychologically devastating for survivors. Humans depend on predictable cycles to maintain mental health and social organization. When time itself becomes chaotic, when you can't predict whether tomorrow will be longer or shorter than today, whether next month will be hot or frozen, the psychological framework that allows people to plan, hope, and maintain sanity begins to crumble. Children born into this world wouldn't just face physical survival challenges, they'd grow up without the basic temporal rhythms that shape human development. How do you teach a child about seasons when seasons don't exist? How do you explain day and night when the length of each is constantly changing? How do you maintain cultural traditions when the time cycles they're based on have ceased to function? The breakdown of temporal regularity would accelerate social collapse in ways that pure physical destruction couldn't achieve. Humans can rebuild cities, replant crops, even adapt to climate change over time. But we can't adapt to the complete breakdown of time itself as an organizing principle for existence. Religious and philosophical systems would face challenges that no human belief system has ever been designed to handle. Most religions incorporate cycles of renewal, seasonal celebrations, and the promise that difficult times will eventually give way to better ones. But what meaning do these concepts have when the physical universe no longer supports the idea of renewal or cycles? The concept of hope itself, which depends on the belief that the future can be different from the present, would become difficult to maintain when every day brings evidence that the underlying systems supporting existence are continuing to decay. This isn't the kind of challenge that can be overcome through human effort or ingenuity. because the problem exists at a level of physical reality that no technology can address. And yet, human nature suggests that even in such circumstances, people would continue to create meaning, to form relationships, to tell stories and make art. These activities wouldn't change the outcome, but they would represent something irreducibly human: the insistence on creating significance even when the universe itself seems to be falling apart. Small groups of survivors might develop entirely new forms of culture adapted to temporal chaos. Instead of calendar-based celebrations, they might mark time by geological events: the opening of a new fissure, the cooling of a hotspot, the shift in local weather patterns. Instead of planning for predictable seasons, they might develop nomadic lifestyles that follow the random distribution of habitable zones. These adaptations would represent a form of human evolution happening in real time, not biological evolution, but cultural evolution, at a speed unprecedented in human history. New languages might develop to describe experiences that no previous human generation has faced. New forms of art might emerge to express the psychological reality of living on a dying planet. But even these adaptations would be temporary measures. The fundamental trajectory of planetary cooling would continue regardless of human response. The superheated zones would eventually cool as the fractured mantle loses its stored thermal energy. The dead zones would expand as more regions lose access to any heat source. The chaotic weather patterns would gradually calm into a new kind of stability, the stability of a frozen, geologically dead world. The final stage of this scenario would be something unprecedented in the solar system. A planet that was once alive becoming truly, completely dead, not just lacking in life, but lacking in the fundamental processes that make life possible. Mars is often called a dead planet, but Mars still has some geological activity, some weather, some seasonal changes. What we're describing is something more complete, a world where even the basic physical processes that create weather and geology have stopped functioning. The atmosphere would eventually settle into static layers as temperature differences disappear and convection ceases. The oceans would freeze from the bottom up as geothermal heat sources fail, creating ice sheets thousands of meters thick. The surface would become a landscape of frozen ruins, the collapsed remains of mountain ranges, the dried beds of ancient rivers, the scattered debris of a civilization that once believed it could master its environment. And through all of this, the sun would continue to rise and set, following the same path it has travelled for billions of years, illuminating a world that no longer responds to its warmth. The cosmic dance of planets and moons would continue unchanged, indifferent to the fact that one small world had lost its internal fire and slipped quietly into the long, cold night of geological death. This is perhaps the most humbling aspect of our thought experiment. It reveals how utterly dependent we are on processes that operate entirely outside human influence or understanding. We can split atoms, sequence genomes, and send spacecraft to other planets, but we cannot restart a planetary dynamo or reheat a cooling core. We are, for all our technological prowess, passengers on a geological machine that we neither built nor control. The cooling of Earth's core would strip away every illusion of human dominance over nature, revealing us as what we really are, a brief flowering of consciousness on a small world that happens, for now, to maintain the precise conditions necessary for complex life to exist. We are not the masters of Earth. We are its temporary beneficiaries, completely dependent on systems so vast and fundamental that we rarely even think about them. Yet this dependence, this fragility, doesn't diminish the significance of human existence. If anything, it makes it more precious. Every moment of stability, every breath of clean air, every day when the ground stays solid beneath our feet, represents a cosmic gift of unimaginable rarity and value. The fact that we can contemplate our own cosmic insignificance, that we can imagine the death of our world and in doing so appreciate its life, suggests something remarkable about consciousness itself. We are matter that has become aware of itself, temporary arrangements of atoms that can contemplate the universe and find it beautiful, even knowing that our time within it is limited. In our cooling core scenario, even as the last humans faced the final breakdown of their world, they would still possess something that no other known phenomenon in the universe can claim: the ability to understand what was happening, to find meaning in meaninglessness, to love and create and hope even in the face of absolute finality. This capacity for meaning-making in the face of cosmic indifference might be the most extraordinary thing about our species, more remarkable than our cities or technologies or art. We are beings who can face the end of everything and still insist that something matters, that the brief moment of warmth and stability we've been given has value that transcends its temporal limitations. And so, as we contemplate the impossible scenario of Earth's core cooling instantly, we're really contemplating something deeper: the nature of existence itself, the incredible unlikelihood of the conditions that allow us to exist, and the preciousness of the moment we find ourselves in right now. Because right now, as you're listening to this, the core is still spinning. The magnetic field is still protecting you. The ground is still solid. The seasons still change in their ancient rhythm. The vast machine of Earth continues its 4 billion-year dance, maintaining the delicate balance that makes your existence possible. This moment, this breath, this heartbeat exists because of forces you cannot see, understand, or control, operating in perfect harmony thousands of kilometers beneath your feet. It's a miracle disguised as ordinary reality, a cosmic impossibility that we've learned to take for granted. The cooling core scenario forces us to see this miracle for what it is. Not a guarantee, not a right, but a gift of staggering improbability and infinite value. Every day that the core keeps spinning, every night that the magnetic field holds steady, every season that arrives on schedule is another page in the most remarkable story ever told. The story of a universe that somehow arranged itself, against all odds, to support consciousness, wonder, and the capacity to contemplate its own existence. And here's what makes this realization even more unsettling. We're not just talking about the end of human civilization, we're talking about the end of the very concept of a habitable planet. Because what we're witnessing in this scenario isn't just the death of Earth's biosphere, it's the fundamental transformation of our world into something that has never existed before in the known universe. You see, when astronomers look for potentially habitable planets around other stars, they use what's called the Goldilocks principle. Not too hot, not too cold, just right for liquid water to exist. But this assumes that planets maintain their habitable conditions through some form of internal stability. What our cooling core scenario reveals is that habitability isn't just about distance from a star or atmospheric composition. It's about having an active, living planet with internal processes that can maintain stability over geological time. Earth with a cold core wouldn't just be uninhabitable. It would be something entirely new. A world that once supported the most complex biosphere we know of, then lost the fundamental requirements for life to exist at any level. Not gradually, through stellar evolution or asteroid impacts, but suddenly, through the failure of its most basic operating system. The psychological impact of this realization extends beyond just the people living through the catastrophe. It challenges our entire conception of what planets are and how they work. We think of worlds as either dead, like the Moon, or alive, like Earth. But this scenario creates a third category: worlds that have died after being alive, carrying the fossilized remnants of complexity in a geological tomb. Imagine the archaeological record this would create. Billions of years from now, if some other intelligence ever visited the cold, dead Earth, they would find layers of sediment that tell an impossible story. Evidence of a thriving biosphere suddenly cut short, not by external catastrophe but by internal failure. Cities fossilized in mid-collapse, forests turned to stone while still reaching toward a sun that could no longer warm them. The stratification would be unlike anything we see in normal geology. Instead of gradual transitions between different eras, there would be a sharp line. Below it, evidence of billions of years of life and geological activity. Above it, the sterile remains of a world that lost its ability to sustain the processes that make planets dynamic. But here's what really keeps me awake thinking about this scenario: the time compression. Geological processes that normally take millions of years would happen in months. The rock cycle, where igneous rock becomes sedimentary rock, becomes metamorphic rock and back again, would accelerate beyond anything we've ever observed. As the mantle cools and solidifies, enormous pressure waves would ripple through the planetary interior. These waves would compress and heat rock in ways that could create entirely new types of minerals, geological formations that exist nowhere else in the solar system. The Earth would become a laboratory for extreme materials science, creating substances under conditions so intense and unusual that they might not even be stable once the pressure subsided. The magnetic properties of these new materials could create bizarre effects as they cool. Instead of a single magnetic field generated by the core, you might have thousands of smaller magnetic anomalies scattered across the surface, each one created by the unique mineral compositions formed during the collapse. The resulting magnetic landscape would be chaotic, with compass needles spinning wildly as they encounter field reversals every few kilometers. These magnetic anomalies would interact with any remaining atmospheric particles in unpredictable ways, potentially creating localized aurora phenomena that appear and disappear randomly across the surface. The night sky would become a constantly changing light show, beautiful but meaningless, as the last gasps of Earth's magnetic personality play out in the thin air above a dying world. Navigation would become impossible, not just because of infrastructure collapse, but because the fundamental reference points that life has used for millions of years would no longer exist. Migrating birds, if any, survived the initial chaos, would find their internal compasses useless. Sea turtles would be unable to navigate the altered magnetic landscape of the ocean floor. Even bacteria that orient themselves using magnetic fields would lose their way. This navigation chaos extends to human technology as well. Any GPS satellites that somehow survived the initial electromagnetic storms would be useless because their positioning algorithms depend on predictable magnetic field corrections. Radio communication would face interference from the scattered magnetic anomalies. Even simple compass-based navigation would become impossible as the magnetic landscape shifts unpredictably. The loss of reliable navigation would be more than just an inconvenience for survivors. It would represent a fundamental severing of the connection between life and the planetary systems that have guided biological processes for billions of years. The very concept of direction, of knowing where you are in relation to where you want to go, would become meaningless in a world where the reference points themselves are constantly changing. But let's dig deeper into what this means for the human experience of space and place. We navigate not just physically, but psychologically, using landmarks and familiar patterns to orient ourselves mentally and emotionally. When the landscape itself becomes unstable, when mountains disappear and new thermal features appear randomly, the psychological maps we use to understand our place in the world become useless. Survivors would face a form of existential vertigo unlike anything in human experience. Not just the disorientation of being lost, but the deeper confusion that comes when the very concept of place breaks down. How do you feel at home when home is a constantly shifting, unpredictable environment where the ground itself can't be trusted? This spatial disorientation would compound the temporal chaos we discussed earlier. Humans need both spatial and temporal reference points to maintain psychological stability. Remove both simultaneously, and you create conditions that no human psychology has ever been designed to handle. The result would be a form of cosmic agoraphobia, a fear not just of open spaces but of space itself, as a concept that no longer provides reliable structure for experience. Children growing up in this environment would develop completely different relationships with concepts like here and there, near and far. Their cognitive development would occur in a world where the basic spatial categories that shape human thinking are unreliable. This could lead to new forms of human consciousness, adapted to flux rather than stability, but at the cost of losing connection to every form of human culture that has ever existed. The social implications are staggering. Human communities are organized around shared spaces, towns, cities, neighborhoods, gathering places. When space itself becomes unreliable, these social structures lose their foundation. How do you maintain a community when the place where you've agreed to meet might literally disappear into a crack in the earth? Governance becomes impossible when there's no stable territory to govern. Property rights become meaningless when property itself is subject to random geological redistribution. Even the concept of borders, whether national or personal, loses meaning when the landscape is in constant flux. Legal systems would face challenges that no jurisprudence has ever contemplated. How do you enforce contracts when the locations specified in those contracts might no longer exist? How do you maintain ownership of land when the land itself is unstable? How do you establish jurisdiction when there are no reliable boundaries? The economic implications are equally profound. All economic systems depend on some form of spatial organization: trade routes, resource locations, production centers, markets. When these spatial relationships become unpredictable, economic activity becomes impossible to organize at any scale larger than immediate barter between individuals. Currency becomes worthless not just because institutions collapse, but because the entire concept of stored value breaks down when there's no stable context in which value can be stored or exchanged. Gold might maintain some intrinsic worth, But what good is gold when you can't safely travel to trade it, and there's no stable location where trades can be conducted? The breakdown of economic systems would accelerate social fragmentation in ways that pure survival challenges couldn't achieve. Humans can cooperate in the face of scarcity, but cooperation requires some form of predictable structure for organizing collective action. When space and time both become unreliable, the foundation for any form of social organization beyond the family unit disappears. Yet even as these large-scale structures collapse, human creativity would likely find new forms of expression. Art created in response to spatial and temporal chaos would necessarily be unlike anything in human history. How do you create lasting works when the concept of permanence has lost all meaning? How do you develop aesthetic traditions when the environment they respond to is in constant flux? Perhaps art would become entirely performative, existing only in the moment of creation because nothing else can be counted on to persist. Or perhaps it would become radically minimalist, focusing on the few elements of human experience that remain constant even when everything else changes: breath, heartbeat, the play of light and shadow. So there you have it. The complete annihilation of everything we know, everything we've ever built, everything we've ever dreamed of, all because a ball of molten metal thousands of kilometers beneath your feet decided to take a permanent coffee break. The magnetic field collapses, the ground caves in, the weather goes insane, and time itself becomes meaningless. It's the ultimate reminder that we're not the masters of this planet. We're just along for the ride on a geological roller coaster that's been running smoothly for 4.5 billion years, and we better hope it keeps running smoothly for a lot longer. Because the moment it stops, we're done. Game over, no respawn. So maybe, just maybe, we should spend a little more time appreciating that miraculous furnace spinning silently in the darkness below, keeping us all alive without asking for so much as a thank you.